Okay, we're going to go finish off the simplex implementation. So we did a lot of this stuff, but basically we're saying a feasible vertex is defined. Now you should know a little bit more about what's on this summary. It says you're defined by a linear system, A prime. Now A prime are rows you're picking corresponding to the tight constraints, right? There's going to be n tight constraints, and you're going to have n rows. And now remember, you have n variables, so this A prime is an n by n matrix. And you have your original B, which is a subset of the constraints that correspond to those rows, the subset of the right-hand sides. And the zeros there are because some of the constraints we're actually using in this linear program are xi is greater than 0. Okay, and that's what we're setting the equality. Okay, so, right, we have this linear program which is ax is greater than b, and x is greater than or equal to 0. So remember, at the origin, where we start, is we just set all the xi's equaling 0. So we're thinking of these constraints as being the tight constraints. Okay, the ones that are satisfied with equality. Tight means the constraints that are satisfied with equality. There's n of them. When you have n of them, you can solve this linear system, and that tells you a vertex. So you begin at the origin. We're assuming now that the origin is feasible, and you move to a better neighboring vertex. Now, a neighboring vertex in this algebraic world is dropping a constraint and adding a constraint into this A prime. That's all it's doing. And then solving for inequality. Okay? So, and now I'm going to show you, I'm going to talk about this coordinate system being this distance from tight constraints. So that's going to be our new coordinate system. So I'm going to say for each one of the tight constraints, how far am I from it? And now if I have n of these equations, that tells me exactly my point. Okay, so that's another thing. We'll go over that. The vertex is at the origin in the coordinate system because the vertex is a place where all the constraints are satisfied, meaning the distance from each constraint is 0. You're on the constraint. Okay? So your representation in this coordinate system is how far you are from each one of those constraints. For a vertex, you're 0 from all those constraints. So all your values are 0. So in this coordinate system, you are at the origin in this coordinate system. Okay? And then I'm going to show you that you can sort of do all this bookkeeping in order mn time. Typically, if you want to solve a system A prime x is equal to something, it takes theta of n cubed time or something, right? It takes some n cubed time. This is sort of more or less n squared time. So each step only takes sort of the size of your problem. Okay? And by the way, this is not really it's really linear. M times n, it looks like you're multiplying two things, but that's the size of your linear program. It's the number of entries in your constraint matrix. So it's actually the total number of entries. Okay? So then we're going to talk about this greedy max flow, which is a new problem. And what we're going to do is try to maximize the flow between 2 points in a network where we have capacities on the edges and you're trying to flow as much material as you can, where you can't overload any link. Maybe like the electric company. The electric company has a different cost model, but one that involves fires at this point. But so we'll go over this algorithm. And the basic idea here is if you want to route flow from A to B, well, you just find a path from A to B, and you send some flow along that path. So that's the basic idea. And then once you've used up that path, you try to find another path. That's the idea, the max flow algorithm. And, okay? So in the two tasks, for a simplex algorithm, you want to say, when you're at a vertex, is it optimal? And you also want to decide which vertex to go to next. Okay? So this is the canonical LP. Okay, so AX is less than or equal to B, and X is greater than or equal to 0. What we're going to do, again, look at this linear algebra form here. There's AX is less than or equal to B, X is greater than 0. So what I'm going to do is I'm going to pick n of these constraints to be tight. At any point, that's what the simplex algorithm is. It's at a vertex. It chooses these constraints. And there's two kinds of constraints. AX is less than or equal to B, and X is greater than or equal to 0. To start the linear program off, I'm going to start with the set of constraints X is equal to 0. And there's n of those. For every X it's equal to 0, you have no room to do anything. You know the point where you're at. It's at the origin. The origin means all zeros. Okay? Okay, when is it optimal? Right away, how do I know the origin is optimal? What did I say last time? Okay, if all the CIs are less than or equal to 0, then I shouldn't, this is great. If AX is less than or equal to B, if this is feasible, and X is greater than 0, if all the C's are less than 0, increasing any XI value decreases the value. And you can't make the XI be negative, right? Because that's what the constraint says. It has to be positive. So that's optimal. So right away, you can tell if something is optimal, at least if the thing is all zeros in this coordinate system. So if there's a CI that's greater than 0, then you know you have to do some work. And in some sense, it's not optimal. So you're done with task 1. So you know whether you're optimal or not. Or you don't, at least here you have a proof you're optimal. You might be optimal here too, but you haven't proven it. Okay, so obviously what you want to do is if you're at the origin and one of the CIs is positive, that's a good direction to go. So the constraint you have that keeps it from being positive is xi is equal to 0. So you can drop that out. You can say xi doesn't have to equal 0 anymore, and we can increase xi. Okay? Until you hit another constraint. Okay, so this is the algorithm again in words. Now you have to implement it in code, and we'll sort of describe. I'm never going to get to code, but I'll show you, right now, this is trivial code, right? You can just all write this for all CI, or they get less than 0, I'm optimal, right? Okay. So I'm going to get to a point where you could write code. Okay? So xi is so you go until you hit another constraint. You raise the xi as much as you can. And now when you raise the xi, this ax is less than or equal to b may get violated, right? Some value you may violate one of the constraints. So whichever the first one you hit by raising xi, you stop there. Okay? Okay, so then you get a new constraint. So you dropped one constraint, you got a new constraint. So you have n constraints or n equations and n unknowns. So therefore you have another vertex. Okay, so here's an example. Here we're starting at the origin. We relax the constraint that x2 is greater than or equal to 0. Why do we relax that one? It was arbitrary. I chose it because the multiplier for x2 is 5. So you get more value by raising x2 than you do by raising x1, right, per unit. But it's arbitrary. There's no particular reason. So I said x2 is equal to 0. So then I start raising it. And I say, well, how high can I get? Increase x2 until inequality 3 gets tight. Okay? If you raise x2, once x2 becomes 3, you can't raise x2 anymore. Okay? It's not tight for the other two equations. Right? What I'm saying is equation 3 becomes tight because x2, once it gets to 3, it happens with equality. Negative 0 plus x plus 3 equals 3. The other two are still loose. Okay? So now you have two new tight constraints. So you're at a new vertex. You have n dimensions where n is 2, and you're at the intersection of two lines, these two lines, where you set the right-hand sides to equal to you set the inequalities to equalities. Okay, so you have a new vertex. You went up to 0 and 3, got a lot more value. This is all good. So this is really quite easy. Just increase one variable. Is it easy to check which, for all the constraints, is it easy to check to tell which one's tight? Yeah, you just look at the coefficient and how much slack you have in that equation, right? Like if whatever, you can just divide x2 by the coefficient of x2 by 2. And you know x2 can't be bigger than 4.5, and this equation would, if it was, this equation would no longer be satisfied. Right? It's fairly easy to see when these equations are satisfied. Okay? Okay, so that's all fine from the origin, but now it becomes a little more complicated because we're not at the origin. So we're going to do a new coordinate system. And as I said in the first slide, the coordinate system is going to look like this. Those should be, I hope those are right angles. So if you take any point, okay, if you're at the intersection of these two constraints, where are you at? Well, you're at the intersection. You're at the point at the top. Okay? But, so in this coordinate system, the point at the top is trivial to compute, right? It doesn't matter, right? But that's not what I'm saying. I'm not saying say what the point at the top is. I'm saying I'm defining a set of variables or coordinates. Okay? And these coordinates are y1, y2, and to represent my whole space. I'm just changing my coordinate system. Okay? And so the coordinate system, so for some arbitrary point in my space, this is what my x is here. I'm saying the coordinate for that is whatever its distance is from x, from this first constraint, that's y1, and whatever its distance is from the second constraint, which is y2. Okay, so that's a new coordinate system, right? Okay. So yi is the distance from constraint I. Okay? Now, how can you write it in terms of the axis? Okay? This is how you do it, right? yi is the distance. What is this constraint? The ith constraint is ai times x is equal to bi. Okay? Now, the distance from that, if you're on this constraint, if your point x is on this constraint, ai x equals b, that's just equal, right? That's 0 if it's on the constraint. yi is 0. If it's off the constraint, this is how far you are from the constraint. And now you could be in the positive direction or the negative direction. Okay? Does that make sense? So it's easy to write down this coordinate system. Right? Very easy. Okay. Recall that for the origin now, xi was the distance from constraint xi is equal to 0. So this is all analogous. When I'm saying this coordinate system, it's not different than what I did in the first place. In the first place, I said the original coordinate system is just a difference from each one of the xi is equal to 0 constraints. Okay, that's the normal coordinate system you're thinking of. Okay? In the same sense. Okay, now in this new coordinate system, all the yi's are equal to 0. Okay? Does that make sense? Because every one of this point x, the vertex, satisfies all of these equations. So ai times x equals bi. ai is a vector. This is vector dot product, and this is that clear? Okay. Okay, so now let's rewrite the linear program. So we have our original linear program, which is, the variable didn't change, right? Which is y1 equals x1 because we didn't change the x1 variable. y2 which is our new that first constraint is still the same. The second constraint is y2 is I'm just subtracting the left-hand side from the right-hand side. Okay, so I can compute my new coordinate, any new coordinate using my old coordinates. Okay? Now you want to solve for xi's, right? Because now I need to rewrite this linear program in these new coordinates. Okay, so I need to express each of the xi's in terms of functions of the yi's. Is that clear? Okay. So now we plug in for x. So what we do is we solve for x1 and x2, and then we plug in, right? And then, so that's how you plug in the objective function. You just plug in the new expressions. x1 is y1, x2 equals this, right? x2 equals this, and we get it. Okay, so now we get a new coordinate system. Okay, so, and we can do the rest. We can also rewrite the whole linear program this way, right? Every equation is in terms of x1 and x2. We replace them with the appropriate expressions involving the y's, and we can rewrite it all. But let's say we did that, and now we have a new vertex. And now in this new coordinate system, again, do the yi's need to be positive? Why do the yi's need to be positive? For any feasible point, I claim the yi's have to be positive. Yeah. Yeah, because it's AX. It says that any feasible point, let's look at this one. Any feasible point negative x1 plus x2 must be less than or equal to 3, right? So now I'm writing down 3 minus the right-hand side. This should be positive for any feasible point. It has to, this equation 3 has to be satisfied. So that's equivalent to saying this expression is greater than or equal to 0. Okay? So feasible points maintain this condition in this new coordinate system. In the new coordinate systems, any feasible point has y1 and all the yi's there have to be positive. Okay? Okay, so now are we optimal? We know every feasible point only uses positive yi's now. This feasible point, the one we're at, the vertex we're at, has y1 equals 0 and y2 equals 0 for the point in this coordinate system at this vertex. Right? So is this optimal? Are we at an optimal vertex? No. Why not? Is this optimal? Does anybody think this is optimal? Okay, nobody thinks it's optimal, but why isn't it optimal? Yeah. Yeah, the C's, the multipliers of these yi's are not all negative, right? The C's is, the only reason I'm correct is saying not C, because C is going to be confusing because C is the original one. But the multipliers, the new objective function, we already got, this gives you the value, by the way, right? This is the value at this point. We saw before the value of this point was 15. And that makes sense because in this coordinate system, the point we're at is y1 and y2 equals 0. Okay? And now I'm saying, well, it makes sense that we should raise y1. Right? Because if we can raise y1, my objective function will go up. Okay? But, I can't make it, I know that I can't have any negative y1s because then it would be an infeasible point. But now I should try to raise y1. Okay? Okay, so here we are. We're here. We're going to raise y1. Y1 was 0, so we still have this tight constraint 3, and y1 and y2 are non-negative because the constraints have to be satisfied. And you improve by increasing y1. Okay, so if you increase y1, which equation becomes tight first? Okay, so the second equation, okay, y2 right now is what? I guess it depends on what y2 is. y2 is 0, right? So which equation becomes tight? Okay, if we raise y1, raising y1, this equation is never going to be bothered by raising y1, right? How about this? So this equation, when you raise y1, it's y2 is 0, right? So it's easy to check. All you have to do is look at the coefficient of y1 and divide the right-hand side by it. And that gives you the upper bound on how far you could raise y1. Right? That's why it's really nice all the other yi's are 0. You're only raising one y1. So you only need to look at the coefficients of y1 and the right-hand side of each of those equations and divide, and then you can see what the limit is. So I guess it's equation 1 is, which one's is tight here? Okay, y2 is 0, right? So which one's tight? Equation 2, right? I guess that's right, yeah. Okay, inequality 2, right? That gives you an upper bound of 3/2. The other one gives you an upper bound of 7. Okay? Okay, so new vertex, new tight constraints. What do we need to do? We have a new solution, y1 equals 1, y2 equals 0, right? It's a new objective value. We can add, this is the objective value from the previous one. We got some extra benefit. Our new objective value is 22. Okay, so now we have a new linear program. We rewrite again. This is the linear program I wrote before in y's. I can do this again. Now I'm going to just denote the new equations as these. So only one variable changes. All the other yi's are the same. What was z2 is equal to y2, but y1 changed to z1, and z1 is it says equation 2 is tight, so I take the slack in equation 2, or the distance from equation 2. Okay, so y1 is equal to this. We can solve for y1. We can put it in our new objective function. All the zi's are the same. We get this new objective function. Okay, are we done? So it's optimal. Okay? Your questions? Okay. So, yeah.
So is Z1 and Z2 still distances from constraints?
Yes.
Are they different constraints from the Y1s and Y2?
Well, okay, Z2 happens to just be the same as Y2, right? Because Y2 is a distance from some constraint, and we don't change that constraint. So Z2 is just the same as Y. I didn't need to rewrite this. But what we did here is we dropped always when we have it written in this form, the constraints that are tied are the ones that look like this, right? The variables we're working with are 0 at this vertex. They're distance 0 from these constraints. So now what I said is I'm going to allow which one am I allowing? Y1 to grow. So I'm dropping this constraint. Okay? So I'm dropping this constraint and I'm putting in this constraint. Okay? So I'm sort of subbing out the variable for Y1 and making a new variable that corresponds to the distance from this new constraint. All the other variables are the same. They correspond to the constraints they corresponded to before because we're only changing one constraint. Okay? Okay, so in each step, what do you need to do? Okay, you need the LP in coordinate system from the type constraint. You need to rewrite the program in this new coordinate system, right? So when you rewrite it in the new coordinate system, you just need to check the objective function to see if all the multipliers are negative. Okay? Okay, and then now how do you go to a tight constraint along an improving coordinate? We found it because what we said is we just found the one, we just looked at all the constraints and saw which one most limits the value, how large you can make Y1. And we don't even need to worry about these others because they're all 0 in this coordinate system. Okay? Okay, now we express the LP in the coordinate system for the new tight constraint, so that we have to resolve everything. And that's what we did. Okay, and we repeat. Okay, so now what if the origin is not feasible? Okay, here I'm assuming that AX is less than or equal to B where X was all zeros. Right? Maybe A has some negative values, and maybe B has some negative values, and it's just not true. Right? Okay. So how do you find a feasible vertex? So then you want to find a feasible vertex somehow. But maybe there's no feasible vertices, right? Maybe there's no solutions at all. Okay? So the first thing you do is you're forgetting about the maximization function. You just want AX less than or equal to B. That's what a feasible vertex is. You want to find some X where you've satisfied all these equations, and it's a vertex solution. That's the things you need to do. So there's a trick. You just make a new linear program where we say the constraints look like this. Now, if Zi is positive, if I add an extra variable to my linear program, which is Zi, and I want this row times X to be less than or equal to Bi, that's what I'd like. But maybe it's not. Maybe there's no way to do that. So what I can do is I could say AIX minus some positive variable is less than or equal to Bi. And now what I can do is put in all zeros to A and just set the minus Zi to be whatever value I need it to be less than Bi or negative Bi. Okay? Okay, so, and then I want to maximize, I want all these Zi's to be 0 to find a feasible point for the original problem. Okay, so now I write a new linear program where AX minus Z is less than or equal to B, and then I want to maximize the sum of I want to minimize the sum of the Zi's, which is maximizing the negative sum. Okay, I'm just writing it in the max form. I want to make all these, I would like to find a feasible point X, I'd like to find a solution where all these Zi's are 0. Okay, so I want to minimize their sum. Okay? Now the vertex, now if you have a vertex solution xz of value 0, all the Zi's are 0. And so all the inequalities are satisfied. And X is a feasible vertex of AX less than or equal to B. Okay? So that's how you deal with the fact that to find the first feasible vertex. That's how you start. So in general, to solve a linear program, you need to solve 2 linear programs. One to solve the feasibility problem, and then from there you need to do the maximization problem. So, this is actually something that actually happens a fair amount in practice. Okay, so there's also degenerate vertices. So what could happen here is I could be at this point, right? Instead of it being at the intersection of 2 lines, it's the intersection of 3 lines. So if I keep trading out the vertices, I could just stay here. I could choose 2 of them and then move to the other one and move to the other one and move to the other one. So you have to do something to sort of make sure you don't go in an infinite loop, right, for these degeneracies. So there's a rule, and you can do it, but that's one thing you can do. The Bland had a way to do this based on the indices of the constraints. But another thing you do, you just move them a little bit, and it's very, very unlikely they're going to land on top of each other. So that's another thing that people do in practice. Okay? And finally, there's this problem that here's this linear program. I want to be below this I want to be in the positive orbit. I want to be below this constraint and below this constraint here. The fact is, it could be that the objective function is this way. So what is your objective function? It's infinite, right? You can just go forever. Okay, so you can't find a vertex solution, but what will happen somewhere in the simplex once you're here, you say, well, look, I can move this variable in this coordinate system. I can grow it, and there's no upper bound. So you'll be able to tell if it's an unbounded problem, right? Remember, right, what happens when you're at this vertex, what do? You say, which one of the variables should I raise? It'll be the one that's the distance from this line, and it says you can raise that thing forever. Okay, so again, let's think about the runtime now. Again, these are all ways for you to kind of understand the algorithm a little better. Okay, you want to check the optimality. That's just checking all the coefficients of the objective function and see if they're all negative. You want to find a tight constraint. You just find that was easy because what happens is you just scan up until you do this thing where you divide the right-hand side by the coefficient of the variable, and that tells you which constraint is tightest. Okay? You want to find a new coordinate system. You sort of need to rewrite the LP in this new coordinate system. And that's probably going to take a long time, right? We have these yi's equals bi minus aix. You have all these new variables, and you want to solve for the x's. So you can plug back in the original linear program to make it be in terms of y's. Okay? So rewrite in terms of y's. You need to solve for the xi's in terms of yi, and you need to plug in. So naively, this is an n by n system. You can do it in O of n cubed time, or there's better ways. But the point here now is all the variables were the same except for one. You only changed one variable. So in that case, you could do it much more. You already have x in terms of all of these other yi's. You're only changing one of the yi's. So it's actually fairly easy. It's kind of like back solving. When you solve a linear program. When you do Gaussian elimination, you do back solving, and you can solve it really quickly. Okay? Okay, now the final thing for runtime bound. So this says it's order nm time per step, per simplex step. And this looks like it's bad because you're multiplying 2 things together. But the size of your linear program is order nm. Right? There's n rows, there's m equations. Each one has possibly n variables in it. So this is very fast. So the simplex algorithm has a very fast step. But now how many steps are there? It could be large. It could be exponential. So it's like a real problem, actually. But in practice, it doesn't go fast. It goes very fast. And in fact, there's proofs that it goes pretty fast if you perturb the linear program a little bit. Okay? So it's called smooth complexity. But you can prove that typically it's going to be fast. Or even if you're given a linear program and you move it around a little bit randomly, you just change the constraints by a little bit, it'll also be fast. Okay? Okay, so now where's the dual? This is extra. This wasn't in the book. So in some sense, I told you so much about duality, and then here's this linear program, way to solve the linear program, and we never saw the dual. Aren't you sad you didn't see the dual? No? Okay. I'm kind of sad I didn't see the dual. Okay. So the coefficients of the coefficients of the optimization function, those are the dual. Those are the solution to the dual. Okay? Who believes that? I mean, one thing about them is they're all negative, right? So it's not really it's the negations of the coefficients, because the dual, remember, the dual variables have to be positive. So the negations of those are actually positive, and that's the dual function. So, I mean, this is kind of the proof. You have a new coordinate system. Say A prime is the matrix of tight constraints. So X is equal to this A inverse of B minus B prime minus Y. Now, when you write out the objective function, you get this thing. I'm just multiplying C times this X. That's all I'm doing. I'm just replacing the X with this thing and multiplying it out. This is a constant. This is just a number, right? A is a matrix with numbers in it. B is a matrix with numbers in it. So this is the number. This is the objective value. We saw that before. We saw 15 minus a bunch of things. Okay? Now this thing is C. It's C. This is vector C times this A inverse times Y. That's all that is. And that is a vector of coefficients, right? C times A inverse times Y. C times A inverse is the vector of coefficients. Okay? So now I'm claiming these are the dual variables. This gives you a solution to the dual program. Now, first of all, I said we stop at optimality if all of these are positive. Okay? So I have the fact all are positive at optimal. Okay? So I get a dual solution here where all the values are positive. Now, finally, I need that AT times Z is greater than or equal to C. That's the feasibility condition for the dual. And so now I multiply AT times Z, A prime T, and then I get this inverse, and I get A prime T times Z is equal to C. Okay? Which tells me that these dual variables actually kind of solve the linear program. Now, there's a problem here because A prime is really just a subset of the original matrix. It's some columns. But all you do for the ones that aren't there is you just make those dual variables be 0, and they don't upset this inequality. Okay? So that you get a dual solution out of it. Now, this is not something that's in the book, but I just wanted to sort of say, not only do you get to read off the optimal, this simplex algorithm also gives you a way to read off the dual solution. You just read it off from your objective function, your final objective function. Okay? So that's nice. Okay, so now we're going to talk about this thing called max flow, which is this problem. Okay, so there's a flow network. I wanted to introduce it. I know I'm going a little quick. I wanted to introduce it because you have it on your discussion tomorrow. So, yeah.
I have a question. So is it possible that your constraint can be in such a way where you have a variable that has a positive multiplier, but you can't increase it?
Yes.
So in that case, what would happen with a good dual? Because then you wouldn't have
Well, what you would do is you would pick a subset of the constraints that gives you
I'm saying you can't get to the state where all the multipliers are negative.
You can. I mean, you can. Yeah, you always can.
Is there an intuitive way to prove that, or is it?
I don't know right now. Yeah, maybe. Yeah, I think you can. Yeah. He's asking because of this like degeneracy or something like that. Because can you always get to a place where the dual variables are positive or negative? You can always get to a place where the dual variables are either negative or 0. Okay, you can do that. Okay. Okay. So here's a flow network is a graph, and capacities on the edges. So this is a picture. So there's a graph, a directed graph, and there's capacities on the edges, right? So the capacity from S to A is 4. The capacity from D to T is 4. How much flow can you send from S to A to D to T? If I want to send 1 unit of flow, 1 is the answer, but how much flow can you send from S to A to D to T? Well, you have to send, you could send 4 from S to A, but then it gets stuck at A. Okay, you're not allowed to stick stuff in the middle. You have to send all the flow from S to T. The middle guys can't have anything left in them. Okay? So and moreover, you can't send more than whatever this capacity is. Like from A to D, the capacity is 1. You can't send more than 1 unit of flow there. And you want to send as much flow as possible. Okay? So that's what these constraints are telling you. It says, I want to find a function, f of e. I want to find a solution where no flow on any edge. It's an assignment of flows to each edge in the directions that they are. So that should be no larger than the capacity, and it can't go in the opposite direction. Okay, because they're directed. Now, finally, if one of these vertices is not S or T, the flow in should equal the flow out, because you don't want flow to get stuck in the middle. Okay, that's what this says. It says the flow coming into a node U is equal to this flow coming out of the node or vertex U, right? This is a sum over all edges that are incident to U, and this is a sum over that are going out of U, and this is a sum over all edges that are going into U. Okay? And now the size of the flow is what? How much flow did you send? There's no flow that gets stuck in the middle. How much flow did you send? It's the flow that you've sent out of the source. Okay? So you sent the flow. The size of the flow is the sum of all the flow out of the source. Why do I not need to think about the sink? What is the flow out of the source? Where must it end up? At the sink. Because it can't end up anywhere else, and we never lose any flow. Right? It doesn't end up in the middle because the flow ending up at each one of these places is 0. Okay? So the flow out of the source is what you're maximizing. Okay? Or you could maximize the flow into the sink if you want. You can go wild, whichever one you want. Okay? Does that make sense? Okay. Okay, so now let's look at this function. Is this function? So this thing says that, right? Here's a possible feasible solution. Okay, so there's a flow function. This is a possible solution. So it says, let's look at this edge. So what this constraint says, my blue number should be smaller than my capacity, which is my black number. Okay? Now this equation says, for each vertex, the flow in should equal the flow out. So what's the total flow in? The total flow in is 3, and the total flow out is the sum of the blue numbers on the outgoing arcs, which is 1 going from C to D and 2 going from C to E. Right? And that's what we're doing here. Okay? So the flow in equals the flow out for all the vertices that are not the source and sink. And this is the total flow out, which is 4. There's 4 units out. Now, I haven't proven that this is the best, right? Okay. Let's look at this. Let's look at this cut. Okay? You see the cut, which is here. Okay? So if you separate it here, how many edges go from left to right? Or what's the total capacity of edges that go from left to right? So I'm asking about capacities. So those are the black numbers. So what's the total capacity that goes from the left part of this network to the right part of this network? Well, from A to D is 1. From C to D is 1. From E to D, that's in the wrong direction. Right? This arc from D to E goes from D to E. So this is not flow you can send from this side of the network to the other side of the network. Right? So you can't use that edge to send flow from the left to the right. And there's an edge from E to T. Okay, so the total capacity of these arcs is 1 plus 1 plus 2, right? And that's 4. Okay? Now, does that look like an upper bound? Is that an upper bound on the maximum flow? Do you think I could do, now that I showed you this particular thing, do you think I could send more flow? No. Right? It's a trivial thing. Another thing, right? Yeah, I mean, you could send 8 units of flow out of S, right? Because that's how much capacity is here. But if you can cut the network apart into 2 pieces, and you one with T on one side and one with S to the other side, the total capacity of arcs going from the side with S to the side to T is an upper bound on the flow you can send. Right? Okay. So this is optimal. So this is what I'm seeking. This is what I'm searching for when I do the The blue thing is the black thing. Black numbers are the problem, and the solution is the blue numbers. Okay? So any ST cut is a partition of V into S and T, where the source is in S, and the sink, we call T the sink, is in T, and its capacity is the total capacity of edges from S to T. And that's an upper bound. Okay, so now here you go. Okay, is this a valid flow? Why not? Why is this not a valid flow? Because this blue number is bigger than this capacity. So not a valid flow. Well, we can fix that. Is this a valid flow? No, because there's 3 units coming in here and only 2 units coming out. So that's not valid. Every node other than S and T have to have exactly 0 net flow into them. Okay? Right. Okay, so there you go. You know the definition. So now we can tell you the algorithm. Okay? In 4 minutes or less. Okay? There's there's the algorithm. It's a linear program, right? All these constraints are linear programs. Okay, they're variables. All the constraints here are linear. We know we can rewrite them in the standard form or whatever we want to do. Okay. Yeah, so there is an integer solution, but this is because this is really a vertex solution is going to be integer. Why is it integer? It's because you're solving a linear system. And when you solve a linear system, you can use Cramer's rule. And remember, you have determinants over determinants. Who remembers that? Cramer's rule? Yeah, you have determinants over determinants. There's a formula. And the denominator is a determinant. And all the determinants are the subdeterminants. It's a subdeterminant. Are like this for this particular matrix. It's just some algebra, but you can prove it. So in fact, there's an integer solution here. Okay? Okay, so now there's another way to do this. Okay, there's an algorithm that you can do that's more intuitive, and actually is telling you what the simplex algorithm does, with all that linear algebra. Okay? So what we want to do is add the flow variables along a path. Okay? And then update the remaining capacity. This is like the easiest algorithm ever, almost. Okay? So here's what you do. So there's a path. I found a path from S to T. How much flows should I send along this path? Not 4, because then I'm going to overload this edge. 1, right? So I can do that. So now if I send 1 unit of flow, can I send more flow along here? No. So my new capacity is 0, right? So now I do it again. Okay, so I can keep doing that, right? So let's do that. Yeah, on the simpler, that's a hard example. So let's look at an easier example. So let's send it along this path. So I could send 1 unit on this, and now my residual, the capacity, how much more can I send along here? Well, I already sent 1, so I can't send more than 1. So how much more can I send? 0. Okay? So this says, is there a path from S to T of positive arcs? No, right? I can't go along this path. I could go here, but that has capacity 0. I'm done. Am I done? Who thinks I'm done? Is this the max flow? Yeah. So this seems like but the optimal is 2, right? It's at most 2 because of a cut. There's 2 in this and 2 in here, right? So this algorithm is broken. Okay? What you could also do, but you could also do something else. You made a decision here. You made a decision to send 1 unit of flow along here. Maybe that was a dumb decision. Stupid, right? Right, you see the solution. I send 1 unit up here and 1 unit here. That's 2. Why was I using this edge? Because I was dumb, okay? So, but, for people who are dumb like me, you want to be able to undo your decisions, right? So what you do is you say, look, I can send 1 unit backwards, okay? I can send 1 unit here and undo this one and send the flow backwards, and now that will be 0. And then send the flow along that edge. So that's what I'm going to add. I'm going to add the ability to undo my stupid decisions. Okay? I'm going to say, look, I sent 1 unit of flow this way. I can undo that. What does undoing it look like? It says, well, sending 1 flow that way. Because if I send 1 unit this way and 1 unit that way, it's 0. Right? So now I define a new graph. where I add these arcs that are in the reverse of any flow I sent. Any flow I sent along an arc, I add a reverse arc that says I can undo it. Okay, and then I try to route flow along this network. And then there's a new path in this network. Look, it says I could send a unit of flow here, and then I could undo this flow here, which is sort of like just sending a flow back and then sending it there. Okay? And now I have 2 units of flow. Okay? So this is a bigger example, and that's it. That's the algorithm. Okay? You have to define this residual network. You can do it this way. I find a path. I add the reverse arcs, and then I continue. Okay? So that's you can see that it works, and you can run the slides at home.
Add ZIs as your additional variables. Just well, you also initialize the first vertex through
Yeah.
this, right? Because otherwise you set an origin.
You might as well set it to all BIs. Yeah.
Yeah. If you set the origin, then you don't. You're not feasible.
Oh yeah, you can't set them at all zeros. Yeah, so you have to start it at that vertex.
So literally, apply simplex